Let's start. I'm going to present you the CHEOPS mission, and I'll, however, start with a short introduction about exoplanets. And we start with how we detect exoplanets, which are the two main methods that are currently used to detect exoplanets, and they are the radial velocity method and the transit method. Just very briefly, what is the radial velocity method? It uses the fact that when there is a planet orbiting around the star is not still. Both objects move around the center of mass. Therefore, also the star moves. And we can see this movement of the star, the changing velocity of the star as the planet orbits around the star in the radial velocity. So in the spectrum, in the stellar spectrum. And we can measure the radial velocity of the star, we can measure this motion, we can measure the periodicity and the amplitude of this motion, and from it we get the different orbital parameters of the system, and most importantly, the mass of the planet, or better, the minimum mass of the planet, because there is also the inclination of the orbit to be taken into account. If we have a lucky geometry and we have a good enough photometric instrument to detect the transit, we have a planetary transit, which is essentially the dimming of light of the star as the planet passes in front of it. And as you can see from this cartoon, the dimming, the size of the dimming is essentially proportional to the size of the planet, and therefore, for measuring how much dimming there is from the planet passing in front of the star during the transit, we can measure the size of the planet, assuming that we know the size of the star. And when we combine the two, then we can get the mass and the radius of a planet, which are essentially the basic physical quantities that we need to have to start knowing anything about the planet. Now let's look at what we know so far. So this is a very simple plot that shows the orbital period of the planets known to date. On the x-axis, and the mass of the planet on the y-axis in Jupiter masses. And you see that where the Earth, Neptune, and Jupiter are essentially located within this plot, and you see different blobs. You see that we have, I hope you can see my mouse, we have the hot Jupiters up here, we have the warm Jupiters more farther out, and then we have super Earths and mini Neptunes here, which is this big blob of planets. Importantly, you see that there are very, very few planets down here, particularly down here where the Earth is, and that's one of the reasons why Plato, for example, has been designed and is being developed and will be launched. This plot is very important for different reasons. It shows structures, and these structures tell us many things about how planets form and how planets evolve. The simplest one to see and also to explain to you is, for example, this gap of planets here. There is a lack of planets in this area of the plot, as you can see, and that's called the subjovian desert. You will see even better in the next plot, which is where with the y-axis in radius. And that's essentially due to the fact that planets, giant planets that form with a nitrogen envelope and end up being very, very close to their host star. If they are too close and their mass is not too high, they will start losing atmosphere very quickly, and therefore essentially planets with time will move from this area of the plot down here, and that's a clear signal of atmospheric evolution that we can then use to study how planets evolve. This is the plot I told you before. This is with period again on the x-axis and planetary radius on the y-axis, this time in Earth radii, and you see again the hot Jupiters up here, and you see then super Earths and mini Neptunes down here. And you see that there are many, many more planets down here at the bottom of the plot compared to the previous one. And that's essentially because we have, Kepler particularly has detected a very, very large number of planets, or small planets that are rather far away from us, and for which it's very, very difficult to measure the radial velocity signal from the host star, and therefore to measure a mass. And that's why you see many planets that have a radius measured and very few instead, or better, much less, that have radius and mass measured. And you see also a large number of planets for which we have a mass and they are pretty far away from the host star, so very large periods. And that's not the case when we look at the radius, and that's essentially because the radius requires a transit, and the probability of a planet that has a very long period to show a transit is very low. And that's why it's very hard to detect transiting planets that are far from the host star. So anytime we find something that's of the order of 100 days and is transiting, it's essentially like Christmas. And then we come to the third plot, which is by far the most important one than when we think about CHEOPS, and that shows the mass on the x-axis and the density of the planets on the y-axis. And you see this very clear trend when it goes to heavy planets, to gas giants, essentially. But then when we go to Neptune, Saturn mass and Neptune mass and lower, we see that the density is very, very diverse. Essentially, for any given mass, we can have a very large range of densities. And that's very intriguing. It tells us, it can tell us many things about planets. It tells us that small planets are very diverse. And then comes the question, why are they diverse? What drives this diversity? What causes this diversity? And that's one of the reasons for which CHEOPS has been built. So now let's get closer to the mission here. This is the timeline of missions that have been developed and are going to be launched in the near future, that are dedicated or have studied or still study exoplanets. And you have a large range of ground-based observatories. And then we have Hubble. We still have Hubble. We had Spitzer. We don't have it anymore. We had Corot. We had Kepler and K2. Gaia, which has done some, is still trying to do. He promised to do to detect lots of planets, and he hasn't done that so far. But hopefully, it's gonna come soon. And then we have TESS and CHEOPS, which are currently the workhorse for detecting planets, and CHEOPS and James Webb, which are the workhorse for studying better characterizing planets. So CHEOPS stands for Characterizing Exoplanet Satellite, and there is actually a second meaning behind the name CHEOPS, and the second meaning will become clear later on in the talk. CHEOPS is the first ESA S-class mission, where S stands for small. The ESA had a second S-class mission, and then after that, it turned into the S-class turned into F-class, which means fast. CHEOPS is a photometer, which means that it measures the luminosity, the magnitude, the brightness of stars with time. That essentially does practically nothing else. It has a telescope of about 32 centimeters as the primary mirror on board. It currently flies at an altitude of about 700 kilometers. It has the size of a very, very big and very heavy, so pretty full fridge. So it's 1.5 times 1.5 times 1.5 meters, so almost 300 kilos. It has a very low power consumption, and that's typical of anything that flies in space. It's just about 60 volt, but it's as much as one of the old bulbs. Given the orbit, the altitude of about 700 kilometers, it has an orbit of about 100 minutes, so it's very fast, orbiting very fast around the Earth. And the mission lifetime is 3.5 years plus n number of years, where n is still unknown. It depends on many things. It also depends not only on the instrument itself, how it behaves, how many maneuvers we have to do on the satellite to move it here and there to avoid collisions with debris. and it also depends on the willingness of ESA to keep the mission alive. CHEOPS is a strange ESA mission. It is not a fully led by ESA, but it is actually a shared leadership between ESA and Switzerland. The PI is in Switzerland, is Willy Benz. The entire mission about 150 million euros, and it has been the cost has been shared almost equally between Switzerland, ESA, and the other countries that are involved. And you see here the other countries that are involved in the mission and what they have provided. One thing that I find very interesting and very nice of this mission is that we have brought outreach directly in space. So there is there has been ESA has done a competition across the countries, across the ESA countries for children drawings. And ESA received very many of those, and a few thousands of those have been selected by a committee, and they have been engraved onto two plates that, and you can see one of them here. These two plates lie on the sides of the baffle of the telescope. This is the telescope baffle, and this is the thing that holds the baffle, the structure that holds the baffle. And here at the side, there are two plates, one on this side and the other one on the other side. And each plate contains several hundreds of these children drawings, and they are in space. They fly together with CHEOPS. You see here two examples of the drawings, and you can see all of them if you go to this link, and you can actually check if there are drawings that are currently flying on CHEOPS that come from any place in Europe, simply by checking by putting in the zip code, the postcode of your interest, and then put it and see whether there is a children drawing that has been accepted coming from that postcode. The interesting thing is that both plates have been essentially attached to the telescope using very highly sophisticated engineering, which is Velcro, and they have been attached by the president of Switzerland, who was at the time, and who had essentially one go at doing it. Because once the plates have been attached, one cannot remove them anymore because of production of dust from the Velcro. So he just had one go at putting those plates, and thank God everything went fine. So this is the position and the movement of CHEOPS in space. So it has an almost polar orbit, is only very slightly inclined. So you see the rear that hosts the solar panels looks always towards the sun, and then the other side, which is the telescope, points always towards night, so in the anti-solar direction. And this allows us to have a view to always look at the sky and always have the solar panels looking at the sun, so that we don't have any power problems. This is the telescope, and you'll understand in a moment why I'm showing you why the movement of CHEOPS and the telescope together. So this is the telescope, the primary mirror that you see here, and the secondary mirror, which is held by these three spikes, these three spiders, these three arms. The telescope has a very extensive and large and long buffer, and that's because the key point of CHEOPS is decreasing scattered light. It's not as much as collecting as much light as possible, because otherwise we would have made a bigger telescope. The entire point is getting precision, and precision requires precision in the electronics, precision in the detector, and reduction of scattered light. And that's why we have this very long and big buffer to try to reduce as much as possible scattered light. Now comes why I showed you the motion of CHEOPS and the telescope one after the other. So what you see here on the left is a CHEOPS image, and you see that all of these triangles, and that's actually why it's called why it is called CHEOPS, because the most famous thing that has a triangular shape is the CHEOPS pyramid. This triangle here, each of those is a star, and the one at the center is the target that CHEOPS is currently observing. So one thing that that's very important to know about CHEOPS is that it's not looking at many stars at a time. It targets one star, so one system at a time, and it stays there for as long as we want. So each of those weird images is a star, and the one at the center is our target. You see that the star, this image, has a triangular shape, and the triangular shape comes essentially from the three arms that hold the secondary mirror. And then you see here at the top, I hope you can see it well. This is a zoom in. This is a so-called imaget. It's a zoom in essentially of it's a different image. It's not this one, but it's a zoom in on the central region of the detector. And you see that there is the target, our target at the center, and then there are other background stars around. You see there are a few, and now you see how this imaget changes with time. So how the stars move in the field of view because of the movement of the spacecraft around the Earth. So as you see that as I move on, the stars around, they move around the target. So the shape stays the same, but the field of view essentially rotates around the center, and that's due to the fact that CHEOPS moves in this way. So it has this motion around the Earth. At the beginning, we thought that might have caused problems, because that might have caused systematics, and indeed it does. It causes systematics in the light curves, but the very nice thing is that this systematic has a very specific time scale, and that's the one of the orbital period of CHEOPS around the Earth. So it can be very easily spotted and then removed by the software. So it's actually very useful for removing the first order systematics and then look for any other systematics that can be present in the data. This shows the bandpass of CHEOPS in comparison to other bandpasses, either typical or from other missions. And essentially, you can see from the plot on the right-hand side that CHEOPS has practically the same bandpass as the Gaia mission, and in fact, the entire CHEOPS machinery runs using Gaia magnitudes. So the entire signal-to-noise calculator is done using Gaia magnitudes. These are just a couple of movies. Yes, also the one on the right is a movie. There is something moving there. It shows the integration of the spacecraft with the payload. So you see the bus on the bottom. That's the one that fixed, is not hanging, and then you see the telescope at the top. So the payload which is being installed onto the bus, and that's the integration. And you see on the right another very important test, which is the vibration testing, that makes sure that nothing breaks down essentially during launch. Very quickly, this is the timeline. So of the entire development of CHEOPS. You see that there are There have been very many steps, but overall it has been a rather quick mission for ESA standards. And the other very important thing that we like to remark every time is that CHEOPS has reached every single milestone on time and on budget, which is pretty remarkable for space missions. And one of the things that that helped us doing this is actually it is a small mission, and yet has been built and developed, keeping all the standards that are required for bigger missions. And then came the 18th of December, and this wonderful thing happened. The launch on a Soyuz from French Guiana. The launch happened happened a day later compared to what was scheduled, and the reason is that there has been a faulty electronic board on the Soyuz, and the Russian engineers. That was a very different world at the time. The Russian engineers that serviced the Soyuz essentially simply exchanged the electronic board during the night, and then launch could occur the day after. CHEOPS hasn't been launched alone. It has been launched together with another satellite, which at the time was an Italian spy satellite. As a result of the orbit of CHEOPS around the Earth, CHEOPS cannot observe the entire sky. So this is the CHEOPS visibility map. You see the right ascension on the x-axis and declination on the y-axis, and you see that essentially we can look mostly along the equatorial plane, and then we can move slightly above and below, but not that much. And from essentially we can see parts of the sky for a maximum of about 2 months or 2.5 months at most. One thing that caused some trouble to us, to the science team before launch, was that we essentially CHEOPS cannot observe the Kepler field, which is here, and that was a bit of a problem at the beginning, because we wanted to look at quite a few. We hope to be able to look at quite a few Kepler targets, Kepler planets, but at the end we could not, and it took a while until we figured it out. Simply because you remember I showed you that the orbit of CHEOPS around the Earth is not exactly polar, is slightly inclined, and that angle of inclination hasn't been fixed for a while. It took a while to be fixed, and that essentially drove the Kepler field out of the field of view of CHEOPS, of the visibility map of CHEOPS. One other thing that is interesting to know is that CHEOPS visibility is essentially orthogonal to the original TESS visibility map. TESS has been constructed to look for most of the time at the poles, and very little at the equator. That was the original design, and then they have found a way to look at the equator too, but at the beginning they essentially could not, and which was very good for us, because we can essentially see at best portion of the sky that TESS can look only for a short period of time. The other thing that you notice from here is that CHEOPS is unable to cover essentially the continuous viewing zones of JWST. So just a slide on how CHEOPS is managed. We have a science team which does the entire management of the science case and takes the scientific data, analyzes them, and publishes them, and tells the SOC, which is in Geneva, what CHEOPS should do. So CHEOPS then takes all our requests for observations and makes a schedule. The scheduling is then sent to Madrid, where the MOC is, and then MOC sends the telecommands on board to CHEOPS, and then CHEOPS sends the data back to the MOC in Madrid, and then Madrid diverts the data to the SOC Geneva again, and to the archive, which is in Rome. So now to the observing program. CHEOPS observing program, at least during nominal mission, which is where we are now, is split in two. We have 80% of the time belongs to the consortium that has built CHEOPS, and 20% of the time belongs to the community. So it is open to the community, which can members of the community can write proposals to get access to CHEOPS. They write proposals to ESA. ESA has a telescope time allocation committee for CHEOPS, and the TAC then allocates time, the remaining 20% of time to the community. The science that the consortium does with CHEOPS is divided into different fields. So the two lion's share of this 80% is between a program that is called MR Improve, or a working group, better, that is called MR Improve, and that aims at improving the measurement of planetary radii of small planets. And the idea there is that we want to improve the measurements of the density to characterize the internal structure and the evolution of these planets. The other lion's share is on the study of the atmospheres of giant planets, of close-in giant planets, and particularly here, what is done are secondary eclipse observations and phase curves to measure the albedo, for example, to then measure winds and possibly the composition and which kind of whether certain planets host clouds and which kind of clouds. Then we have a part which is a small part of the CHEOPS time, of the CHEOPS GTO time, which is dedicated to look for transits of planets detected with radial velocity. So we target planets that we know of, that have been detected previously with radial velocity, and for which no transit has been, for which we don't know whether the planet is transiting or not, and we try to detect whether a certain planet transits or not. Then we have another part of the program that looks at special features of planetary systems, like looks for moons and rings, or tidal deformation of the planets, or, for example, of tidal decay in the orbit of planets. And we have another program that looks for new planets. So it is essentially a search for new planets, or search for other peculiar features like exocomets, for example. And then we have finally a program that is dedicated to everything else, and that's mostly stellar physics, so stellar variability, stellar activity, and we have even done occultations of dwarf planets of the solar system. Now, why is the density? So we know that the density is very important, and it is very important because planets can be very diverse, and that's the density that's going to tell us how a planet might look like. But why do we want to measure the radius very precisely if we are interested in measuring the density precisely? And the reason is very simply lies in the formula, in the mathematical formula for the density, which has the radius at the third power, and that makes the radius more important than the mass. The accuracy, the precision in the measurement of the radius more important than that in the mass, to then finally measure precisely the density. So we measure the radius precisely with CHEOPS, and we hope that radial velocity then measures the mass of these planets, or has already measured the mass of the planet with enough precision, and then we combine the two and finally measure the density. And this is why density is so important. You can have planets that have very similar sizes or similar masses, but in reality they are completely different. One can have a planet that has a giant core, a very big rocky core, so it's very heavy, and very tiny atmosphere that makes the planet small, and that might look identical to a planet that has a small core and a very big hydrogen envelope, but the two planets are completely different. And that's the thing that that measuring the density allows us to figure out, and then we can use these measurements to then run our interior structure models that tell us the bulk composition, which is the approximate bulk composition of these planets, and therefore do a first characterization of the internal structure of these planets. This is just I skipped that slide. This is the very first scientific observation that CHEOPS has done. It was on Kepler 11, on KELT 11b, sorry, and that was essentially just an observation to demonstrate that the CHEOPS is capable to reach all the requirements that has been given. Now, a couple of slides on some of the results that we obtained, and this was a very big surprise. So this is the detection of Nu-2Lu-PD. So Nu-2Lu-P is a system that has been known previously from radial velocity, and TESS, which has launched shortly before CHEOPS, TESS has detected the transits of planet B and C, and that's why we targeted them, because we were interested in measuring more precisely the densities, so the radii and then the densities of these two planets. And during one of the observations, in particular the observation of planet C, during one of the transits that we got this light curve, this very strange light curve, which we realized afterwards was essentially the superposition of two transits, of the transits of planet C, and then this other transit here, which is the one of planet D, which is very, very interesting, because this planet has an orbital period of more than 100 days. And this is exactly one of the reasons for which CHEOPS has been built. Finding planets that orbit very bright stars, and Nu-2Lu-P is one of them, is a very, very bright star, and that can become primary targets for transmission spectroscopy observations in the near future, particularly with JWST. And the Nu-2Lu-P system, and in particular the Nu-2Lu-PD planet, which is far away, rather far away from the host star compared to other transiting planets that we have, is an ideal target. It has a big atmosphere. It is not a very big planet. It has, however, an extended atmosphere. Orbits a very bright star, and that makes it ideal for atmospheric characterization. From the CHEOPS measurements and the previous mass measurements, are putting everything together, these are the kind of results that we obtained. So these are very complicated plots. I'm not going into the detail. You can go and look at them in the paper if you're interested. But these are essentially the results, the key results that we obtain on the internal structure of the three planets, and on the atmospheric evolution of the three planets. You see here the posterior probability distribution function for the rotation rate of the host star when the star was young, and the posterior probability distribution functions for the initial atmospheric mass fraction of the three planets. And for example, for the B planet, we obtained that the B planet has been completely stripped of its atmosphere by the host star. The C planet has experienced some atmospheric escape, while the D planet still hosts its primary atmosphere and hasn't gone through significant mass loss. Another interesting result was that of the TOI 178 system, which has been originally detected by TESS, which detected a few of the planets. I think they were B, C, and D. And then we started to look at this system as well. And we found serendipitously, like Nutlu-PD, we found it essentially by luck, the E planet. And that told us that or better signaled that this might have been a Laplace chain of resonances where the periodicities of the planets are all connected, are all related to each other. And that prompted us to look at additional planets in the system, and we indeed found more with the periodicities that have been expected. And we went on and looked for more, but we could not find any other. So this is another result that we obtained with CHEOPS. And this is again why it is important to find systems like this. And this is actually my last slide, so I'm almost done. You see the planetary mass on the x-axis and planetary radius on the y-axis, and you see the location of the planets hosted by the TOI 178 system, and you see that there is some randomness in the distribution of the densities of these planets in the system, not only in terms of mass and radius, but also in position. So it's not that as we move out, as we move farther away from the star, planets tend to become more puffy and less dense. That's not the case. There is some randomness here, and that's very interesting for understanding better which is the evolution of these kind of systems or better of planets in general, of small planets in particular. And these kind of systems are very interesting because Laplace resonant chains, they are they haven't been affected by mutual effects, mutual gravitational effects among the planets. Such a system has been is as it is. The orbits are as they are now since the dispersal of the protoplanetary disk. So everything that has happened to the evolution of the system happened either inside the disk or during the evolution, but we know that the orbits haven't changed, and this is very interesting because it can tell us a lot about how these kind of planets evolve with time. And with this, I think I've reached my 40 minutes, and I'll stop. Thank you.